kind of using this this idea that if we do work on the system, we transfer energy into or out of the system. So if we pick up a box, we are taking that stored chemical potential energy in our muscles and turning it into the potential energy of the box. We let the box go from that height, then gravity is doing work on the box. But let's say there's no outside forces. Your hand's not part of the outside system, and gravity is not part of the outside system. So in both those scenarios, we were considering the box itself, and we were thinking anything that was being done to it had an outside force acting on it, and that outside force was causing it to change its momentum. But in fact, if we look at a system where there's no outside forces, then the law of conservation of energy kicks in, which says that the total mechanical energy of a system stays the same unless an outside force acts on it. So when we talk about the total mechanical energy, we're talking about all the different types of mechanical energy it has. So if I am talking about a box that's been lifted up, it could have potential energy or kinetic energy. So the total energy is equal to the sum of those. And that's what we're really looking at, is the total of mechanical energy, the total of the potential energy and the kinetic energy of the system. And regardless of what I do to that system, then the total will always stay the same. So if I lift the box, the sum of Ui and Ki is going to be equal to the sum of UF and KF, which means that however I change the potential energy, the opposite will happen to kinetic energy. Now, we've already talked about that. We said, okay, if we gain potential energy lifting the box and then we let go of it, then gravity causes it to fall and it loses its potential energy, but it gains kinetic energy. So there's a negative change in potential energy, but a positive gain in kinetic energy. So this idea here can be used to simplify our lives and solve problems that are kind of kinematics related without even knowing anything about the acceleration or really much about it at all. So let's say that we have a 2 kilogram ball and it falls 20 meters and we want to know how fast it's going. So here's our diagram. We have a ball and it's going to start at a position of 20 meters and then it's going to fall to a position of 0 meters. And we know that at point A, the U at A plus the kinetic energy at A has to be equal to the U at B plus the kinetic energy at B. But we've also talked about this. When we lift it up, when it starts, its velocity is 0. So its kinetic energy at the top of the 20 meters is 0. So it only has potential energy. And when it falls, right before it hits the ground, it's lost all its height. So now it only has kinetic energy. So the way that we kind of show this mathematically is we start out with TE at A equals TE at B. And we say UA plus KA equals UB plus KB. We know that at Ka, it has 0 kinetic energy, and at B, it has 0 potential energy. So the U at A is equal to the K at B. So we have mgh equals 1/2 mv squared. I noticed that these equations both have m in them, so it doesn't even matter that it's a 2 kilogram ball. If there's no friction in the system, no air drag acting on the ball, then we've already talked about this, that objects fall regardless of their mass at 9.8 meters per second every second. They gain speed. This law is already saying that regardless, the velocity squared is going to be equal to 2gh, or v equals the square root of 2 times 9.8 meters per second squared. And this h here is the h at point A. So that would be 20 meters, making sure all our units are meters and seconds like they're supposed to be. So if I take the square root of 2 times 9.8 times 20, I'm going to get a speed of 19.8. So the speed of it is 19.8 meters per second. Now, let's talk about how we could have solved this with kinematics. If we had solved this with kinematics, it would have started out with an initial velocity of 0. It would have fallen negative 20 meters. Its acceleration would have been negative 9.8 meters per second squared. And we would have been looking for VF. The equation we would have used would have been VF squared equals VI squared plus 2G delta Y. Starting to see a similarity here, 2G times the height, and V squareds. So this would have been 0, VI 0. So VF squared would have been the square, VF would have been the square root of 2G delta Y. No mass in there. So look, we're coming up with the same relationships. For a physics instructor or a physicist, that's really exciting. We've got two different concepts, very different concepts that are coming up with the same mathematical formula to find that answer. This one, I think, is easier in a lot of ways because you really only have two equations, whereas when you do kinematics, you have four equations that you have to pick from. Sometimes you have to do two steps. But this one, you just have one equation with two equations in it. Let's look at another example. Let's look at a roller coaster. So, assuming that there's no friction in the roller coaster, the total potential energy and kinetic energy at A is going to be equal to that at B, to that at C, to that at D. All of these are going to be equal to each other. The total is always going to be the same. So let's use gravity as 10 and let's consider a 1,000-kilogram car. And let's make a little chart here. We're going to look at points A, B, C, and D. We're going to find the potential energy, which is going to be mgh. We're going to find the kinetic energy, which is 1/2 mv squared. And we're going to find the total energy, which is U plus K. So let's look at point A. We're going to start from rest. So if we're starting from rest, then the K is 0. So the only energy that it has at point A is U, potential energy. And that's going to be 1,000 times 10 times 140 meters times 10 meters per second squared. And we're just using that number here in this problem to make it easier. So that's going to be 140 with 4 zeros. 140, 1, 2, 3, 4. Or 1.4 megajoules. Okay? So 1,400,000 joules. If I add these together now, I know that this car has a total energy of 1.4 megajoules. Let's talk about what happens at B. Well, at B, if we had looked at the point here between A and B, How would that be different? How would this be different? Well, if I were looking at this point, all of that potential energy would have been kinetic energy. So the U here would be 0 and the K would be 1.4 megajoules, right? Because all of it would have been converted into that. So when we go up to B now, you still have a total of 1.4 megajoules. But because it is moving, it has kinetic energy, and because it has height, it has potential energy. So the potential energy at B is simply going to be 1,000 kilograms times 95 meters times 10 meters per second squared, which is going to be a 95 with 4 zeros, or 0.95 megajoules. Okay, so you're only going to have 950,000 joules of energy here, but your total is still 140. So if we subtract those from each other, we can find the kinetic energy. And the kinetic energy would be 1401234 minus 951234 would be 4,51234 joules. Okay, so 0.450 0.45 megajoules. Let's just mention that if I know the kinetic energy, I can find the speed, right? If I do the math here, I'd have to multiply both sides by 2, divide both sides by mass, and V squared would be equal to 2K divided by M, which would be 2 times 4.5 e to the 5 joules divided by 1,000. So if I do that, I would get V squared equals 900. And if I take the square root of that, V would be equal to 30 meters per second. So it's traveling at 30 meters per second at that point. When I get up to point C and D, which are both at 80 meters, they both will have the same total energy. And assuming that they're still moving, right? Assuming that they're still moving, that it doesn't lose any speed. The potential energy at C and D would be 1,000 times 80 times 9.8, 10 meters per second squared, which is going to be 80 with 4 zeros. Okay, so it would be 80,000 joules of potential energy, which would leave 60,000 joules of kinetic energy at both of them. Now, let's say instead that the car comes to a stop. So it's going to have a kinetic energy is equal to 60,000 joules at C, and it's going to have kinetic energy of 0. So the force that's doing that will be friction, right? And it's going to do it over a distance of 120 meters. So are you thinking that now this is a system that has an outside force on it, and we can use work equals KE. Work equals change in K. So the work is the force times the distance, and that's equal to Kf minus Ki. Well, the force times 120 meters equals Kf, which is 0, minus 60,000 joules. So if I do this, F is going to be equal to negative 60,000 joules all over 120 meters. And that's going to give us $500. And it's going to be a negative 500 newtons because it's friction force. So we don't want to neglect that negative. It means that the friction is acting in, the car is moving to the right, but the friction force is moving to the left, causing it to decelerate. Now, if we had done this before, we would have been able to say, well, we could have been able to find whatever its speed was at C. That would have been our initial speed. We would have known that Vf is 0. We would have known that x was 120 meters. We would have had to find A and then use F equals ma to find the friction force. The A would have come out to be a negative number, and then we would have plugged it in and multiplied it by the mass of the car, which was 1,000 kilograms, and we would have found 500 newtons in the negative direction. So we could have done it with kinematics and F equals ma, but now we've got the work kinetic energy theorem, which makes it so much easier. And that's conservation of energy.